Okay, so last we spoke, we wrote down the Boltzmann equation. So let's remind ourselves of how that works again. The Boltzmann equation. That said that the probability of finding an atom in energy level E sub B divided by the probability of finding that atom in energy level E sub A, which will be the ratio of the actual number of atoms with energy E sub B divided by the actual number of atoms with energy E sub E, because the probability per atom is going to determine what fraction of the atoms are in a given energy level. And so that will also be the ratio of the populations of those levels. We said that that was the multiplicity or degeneracy of state of energy level E sub B, G sub B, e to the minus EV over KT. Well, the same thing for energy level EA, G sub A, e to the minus E sub A over KT. So we've got the Boltzmann factor in the numerator and the denominator. And so that would be GB over GA, e to the minus E sub B minus E sub A, the energy difference divided by KT. So the bigger the energy difference is compared to KT, the greater the population will be in the upper level state. And so now let's actually use that for something. We will do example 8.1.3. For a gas of neutral H atoms, neutral hydrogen atoms, at what temperature will equal numbers have electrons in n equals 1 and n equals 2? So we can apply this to that. So example 8.1.3. From the book 8.1.3, a fine example which asks, for a gas of neutral, i.e. not ionized, the electron is still attached to the proton, for a gas of neutral H atoms, at what temperature will equal numbers have electrons in n equals 1 and n equals 2? And will those two energy levels be equally populated? N equals 1 is the ground state, n equals 2 is the first excited state. So we need to figure out what GA and GB are. In that case, it's G2 and G1, those degeneracies. Remind me, what is the degeneracy for the different energy levels labeled with the principal quantum number n? For hydrogen, do you remember? So it's 2 in each little sublevel, right? 2 electrons can go in each little substate, right? But, okay, for the ground state, you can have 1s. Can you have 1p? Nope. Because L goes from what to what? L, that quantum number, goes from... No, that's... So you're thinking of m sub s right there. So L, right? You got N, L, M sub L, M sub S, right? N, L, M sub L, M sub S, L. So what are the values of N? N can be, what's the smallest value of N for hydrogen? 1, then comes 2, then comes any n to this? Nope. So N, right, can be 1, 2, 3, da, 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 da. L, on the other hand, goes from
n minus 1 to 0.
Yeah. Mm-hmm. put it as 0 to n minus 1, right? And then n sub L goes from
Negative L to L.
minus L to L, right? It's understood in steps of 1. And then finally, n sub S can be either, yeah, it's plus or minus 1/2. This is the one that says that 2 electrons can fit in any orbital, and these are the ones that are telling us the orbitals, right? So for n equals 1, L can only be 0. That means ML can also only be 0, but the electron can go into either spin up or spin down. So the degeneracy for n equals 1 is 2. Because you can only have 1 comma 0 comma 0 comma plus 1/2 and 1 comma 0 comma 0 comma minus 1/2. So G sub 1 was 2. G sub 2, well then you can have L can be 0 or 1. And when L is 0, ML can only be 0. When L is 1, M sub L can be minus 1, 0, or 1. So that was 1, 2, 3, 4 orbitals, right? In other words, you have n is equal to 2, L is 0, ML is 0, that's 1. N is equal to 2, L equals 1, ML can be minus 1, 0, 1. That's 3 more. So there's 4 substates for n equals 2, 1, 1s, and 3, 2p, when we use the chemistry kind of notation. And the electron can be spin up or spin down in any of those. So there are 4 n equals 2 orbitals, 1, 2s orbital, 3, 2p orbitals. Each can hold 2 electrons. It can hold the electron that's in hydrogen, is only 1 electron. The electron can be either spin up or spin down. So with 4 orbitals, the electron can be spin up or spin down. How many states is that? How many states is that? 8. 8. Right, so G2 is 8. 8, n equals 2 states. How many n equals 3 states are there?
18.
18, yep. So what was the pattern? G sub n is, what was the formula?
2n squared.
2n squared. Right. G sub n is 2n squared, right? That's the general formula. When you make that tree of possible states like we did last time, n, L, n sub L, n sub S, there's 2 leaves, one for each spin on n equals 1. There's 8 leaves on n equals 2. There's 18 leaves, final things on n equals 3. In general, the pattern is it's 2n squared. So we need G2 and G1 over there because we could let B represent n equals 2. A could represent n equals 1. What's G1? No. 2n squared. 2 times 1 squared, 2. G1 is 2. What's G2? Yep, 8. 2 times 2 squared is 8. So G1 is 2, G2 is 8. There's 8 substates for n equals 2, 2 substates for n equals 1. So we're going to need that in this formula right here. And then meanwhile, what's E sub n for hydrogen? To an operative approximation, the energies only depend on n, and they're given by that formula, which, man, you should know. Shouldn't have to look this up. What's E sub n? It's minus how many electron volts over what? Mine? Over what?
1.
Well, I'm in general. What's E sub n?
30.6 over n.
No, minus 13.6 electron volts over, not n, over
Squared.
n squared, yeah, n squared, yeah. That you should know. You should just know that result because it shows up all the time. So E sub n is minus 13.6 electron volts over n squared for hydrogen. And so we need the 2 energies. the A and the B, here A and B1, B and B2. So what's E sub 1? From the formula, what's E sub 1? What's the ground state energy for hydrogen?
13.6 OBC for 4.
For N equals 1.
Yeah, it's just 13.6.
What's its sign? What's its energy? Minus, yeah. E1 is minus 13.6 electron volts. E2 is minus 13.6 eV over N squared, 2 squared, right? Which is, if memory serves, minus 3.4 electron volts. That's right, isn't it? 4 times 3 is 12, so yeah, minus 3.40 electron volts. And so what shows up here is the difference in those energies. So E2 minus E1 will be equal to what in this case? If E2 is minus 3.4 and E1 is minus 13.6, what is E2 minus E1? What's the gap in energy between those? 10.2 electron volts, yep. E2 minus E1 is 10.2 electron volts. The difference in energy, that's the energy it takes to go from E1 to E2. You have to give it 10.2 electron volts. So the electron, if you have an atom in the ground state, you need to give it, a hydrogen atom in the ground state, you need to give it 10.2 electron volts divided into the N equals 2 state. This should be easy for you. So if you're confused by this, you really need to review everything we said about this, because this stuff should really just be trivial for you to work out. And if you're puzzled by it, it means you really need to review all of that. What questions do you have at this point? Yes?
If you're performing an experiment and you're dealing with this,
Mm-hmm.
if we have more or less energy than what is required, let's say 10.2, what would happen to those?
So in other words, here's the thing. In terms of, it's very important to realize that one way to get a hydrogen atom in the ground state up to the electron being in N equals 2 is for it to absorb a 10.2 electron volt photon. Right? When it comes to photons, super picky. Could it absorb a 10.3 electron volt photon, use 10.2 electron volts to get to N equals 2, and leave the rest or something like that? Could it? No. Very picky. It's got to be within a very narrow range because the energy levels aren't perfectly well defined. Within a very narrow range, it needs to be 10.2 electron volts. Collisions don't work that way. If you have a collision and there's enough energy in the collision to give the hydrogen atom, say, 10.5 electron volts of energy, what can happen is that the atom's kinetic energy increases by that much. Or 10.2 electron volts could be used to promote the electron into the N equals 2 level, and it would also pick up 0.3 electron volts of extra kinetic energy. So with collisions, not so picky. And that's important because it means that collisions are the main way that this happens because there's more flexibility with collisions. Yes,
So
go
what
ahead.
happens to the excess kinetic energy?
In other words, it shows up as extra kinetic energy after the collision. So some of the energy in the collision, basically energy is conserved overall in the collision, right? But it could be subdivided so that part of the incoming kinetic energy is used to promote electrons to higher energy levels, which would then mean, okay, the kinetic energy afterwards will be less than, the kinetic energy in the atoms after the collision will be less than it was before the collision because some of the incoming kinetic energy was used to move electrons to different energy levels. And so the total energy will be conserved, but it would show up as an inelastic collision because some of the energy is used to bump electrons to higher energy levels, and that's less left over for kinetic energy of the atoms flying apart after the collision. And so the whole idea here is you've got this gas of atoms. The higher the temperature, the faster everybody's moving, the more kinetic energy is available in collisions. And so that's going to set what fraction of the time electrons that are in the ground state get promoted to the first excited state. And this is how the statistics work out. This is the thermodynamics. In equilibrium, this is predicting what fraction of the atoms would have been bumped into n equals 2 by collisions, and occasionally by absorbing photons, but mostly by collisions. And in equilibrium, remember, every process and its inverse go at the same rate, and that's why overall the number of atoms in each different energy level stays constant to within statistical fluctuations, because any given atom spends some of its time in the ground state, spends some of its time in n equals 2, spends some of its time in n equals 3. This ratio will also be the fraction of the time any given hydrogen atom is in n equals 2 versus n equals 1. It'll also be that fraction. Any individual atom is going between different energy levels, because when it gets into n equals 2, it'll drop down to the ground state one way or another, either by having a collision and then some of the energy shows up after it drops energies and it shows up as extra kinetic energy after the collision, or it can give up a photon dropping down to n equals 1. And overall, the number of atoms entering n equals 2 and the number of atoms leaving n equals 2 are equal to one another at all times, to within statistical fluctuations. So in equilibrium, the populations stay constant with time, to within thermal fluctuations. It's not razor perfect constant, but to within tiny statistical fluctuations, they stay constant. And the more atoms there are in the gas, the smaller the fractional variation is. Just like if you throw 1,000 dice, you'll get closer to 50-50 heads and tails than if you throw 10 dice. Because statistical fluctuations get smaller as the population of things undergoing fluctuations get larger as a fraction of the population. Does that make sense?
Yes.
Okay. What other questions do you have? Yes?
One more.
Mhm.
You said that at every given n equals some state, the number of atoms is equal. The reason we excite them is to have no kinetic energy? That's the goal?
Well, there's no goal here. It's just that sometimes collisions will promote electrons to n equals 2. There's no endeavor here or anything like that. Our question here is, at what temperature will there be a situation in which collisions, etc., have caused there to be equal numbers in n equals 2 and n equals 1? At absolute zero temperature, how many of the electrons would be in the ground state? Of all the atoms, what fraction of the atoms will be in ground state at absolute zero temperature? What would that be?
All of them.
All of them. At absolute zero, there's nothing to excite anybody, so that the system will be in its lowest possible state. So everybody's in n equals 1 at zero temperature. As the temperature rises, some atoms manage to get into n equals 2 because of collisions. The higher the temperature, the more get excited into n equals 2. Now any individual atom won't stay there, it'll quickly drop out of that, but at any given time, some atoms are getting moved up to n equals 2, and an equal number are moving out of n equals 2, and you get an equilibrium situation. Thermal equilibrium is when every process and its inverse are at the same rate. It's what maximizes the entropy as well. You got to take stat mech to see all this more clearly. But at any given temperature, what this is saying is what fraction will be at that higher energy level because of all these interactions, these thermal interactions. And as the temperature increases, this negative exponent gets smaller in magnitude, which means this ratio gets bigger. The higher the temperature, the bigger this ratio becomes. So the question is, at what temperature do we get a situation where there would be just as many in n equals 2 as there are in n equals 1? That's what we're asking. How hot does it have to be to make that happen? Okay? All right, so that's our goal of this problem, is to see what temperature makes this happen. at what temperature will equal numbers have electrons in n equals 1 and n equals 2. Okay? So, all right. We've got our numbers there. We've got E2 minus E1 is 10.2 electron volts. We've got that G2 is 8 and then G1 is 4. So plug it in over here. Plug. Okay, or if I'm more dignified, substitute. So let's substitute here. So this is saying N2 over N1, because here we'll let B be 2 and A be 1, those 2 and 1. N2 over N1 is G2 over G1, e to the minus E2 minus E1 over KT, making things specific to our problem right here. Okay, but what's G2 over G1? G2 is 8, G1 is 2, so what's G2 over G1? It's a very specific number, it is 4. G2 over G1 is 4. And what's E2 minus E1? 10.2 electron volts. So this is 4e to the minus 10.2 electron volts divided by KT. So we should express KT in electron volts here. K can be written such that it's electron volts per Kelvin, so that KT is in electron volts. So can I erase this stuff here? Question? No, it's divided by KT. Thank you. My eye turned that into a, yeah. Definitely divided by KT. Thank you. That's very important. Yes. And it showed up again over here. Yes. It is most certainly divided by KT. Because it needs to be in the denominator there because higher temperatures are going to make that number bigger. And if it were in the numerator, it would not do that. It would make things work. That would be wrong. Okay, can I erase this stuff over here? Okay. So, we want equal numbers. So that means make N2 divided by N1 be 1, so that there's equal numbers in level 2 and level 1, saying N2 over N1 equals 1, and solving for T, that's what we're looking for. What's the magic temperature? Gives, okay, we'll say 1 is 4 times e to the minus 10.2 electron volts divided by KT. So what I'm going to do is flip things over, right? This would say 1/4 is e to the minus 10.2 eV over KT. Turn that around. 4 is equal to 10 to the plus 10.2 EV over KT, right? Put another way, just multiply both sides by e to the plus 10.2 EV over KT, right? And so that gives you 4 is equal to 10 to the power 10.2 EV over KT. I want to undo that 10 to the power. So what's the opposite of, how do you get rid of an exponent like that? What's the opposite of exponentiation? The inverse of exponentiation is taking the logarithm. I'm going to use the natural logarithm, even though this is kind of suggesting to take the base 10 logarithm. And I could, but I'm going to take the natural logarithm. So, because, nobody stop me. I'm joking here. This isn't a 10. What should that be right there? It should be E, so there's no reason to take a base 10 logarithm. What was I talking about? I was being so silly. I should just edit this so that nobody sees that. I probably won't because it's too much trouble. So, geez, I know when you were watching this, Willow, that you were screaming into the computer, but DH, it should be E, not 10. Well, you're right. Very good. Glad you caught that. Okay, so let's take the natural logarithm of both sides. So this says that 10.2 electron volts over K T is equal to the natural logarithm of 4, because somehow I decided to flip left and right when I took the natural logarithm also. And so then this says that T is equal to 10.2 electron volts over K times the natural logarithm of 4. So if we put in the numbers, that's 10.2 electron volts over the Boltzmann constant in terms of electron volt per Kelvin is 8.62 times 10 to the minus 5th power electron volts per Kelvin, which I'll write as eV Kelvin to the minus 1, times the natural logarithm of 4. And so when you put all that into your calculator, notice the EV units will cancel. I've got inverse kelvins in the denominator, so that'll turn into Kelvin, which is better because the end result's supposed to be temperature here. And so you get 86,400 Kelvin. 86,400 Kelvin is the temperature that it takes to produce this result, that you've got an equal population of n equals 1 and n equals 2. And so now I will pop open my laptop and get it going here so that I can show you a plot that shows the population ratio that we're looking for as a function of temperature. And I left my usual laptop at home, so I'll do this other laptop, which means I need this adapter. And it would also help if I turn this on. So all goes well and everything cooperates here. Wake up, little laptop. Hey, you can do this. There we go. Oh, magical. What's my password? It's right now. And I want to extend the screen. Okay. Cracking peanuts? What is that doing?
I'm trying to take this off.
Okay. It sounded like I'm like an Outback Steakhouse and people are like cracking peanuts or something.
There's peanuts at Outback Steakhouse?
Is that the one? No, it's not Outback. It's Texas Roadhouse, I think it's called.
It is a Texas Roadhouse?
Yeah.
I'm so aware of this.
Yeah, they give you like peanuts in the shell and you can crack them. Okay, sure. Yeah.
Did not give me those last time I went. I'm going to ask for them.
Oh, yeah. You should toast do that. Okay. All right. So, if this will behave itself here, go. Okay. There we go. So, this is a plot of N2 over N1 plus N2 for hydrogen using the Boltzmann equation. And in the next homework, you will joyfully make plots similar to this one using Mathematica. it would be much harder to do it via other things. So, I mean, you can do it in Python as well, but I recommend using Mathematica for it, because then you can just nicely define the function in Mathematica and give it a plot range and its energy. So the idea here is, over there, I'll just do this over here, so that Willow can see what I'm writing first, or you can later when you're watching this again, because you can't get enough of it. So what we have found was n2 over n1. How would we find n2 over n1 plus n2? So this is a plot of n2 over n1 plus n2. And the idea here is that n1 plus n2 is, for lower temperatures, this is nearly all the H atoms, because it's the ones in n equals 1 and in n equals 2, and the higher energy levels are harder and harder to populate. So this is nearly all the H atoms at low temperatures. So it's a proxy, a substitute for n, the total number of hydrogen atoms. It's not exactly right, because it's not all of them. Some are n equals 3, 4, and so forth. How can we get that from the Boltzmann equation? Well, we don't get it directly from it. The trick is, notice if I divide through by n1, this is n2 over n1 divided by 1 plus n2 over n1. I just divide the numerator and the denominator both by n2 over n1, and this n2 over n1 we did get from the Boltzmann equation. So, in Mathematica, what you would do is define a function, right? You could define the function n2 over n1 as a function of temperature by plugging into the formula and telling it what k is and so forth. You define a function of temperature by telling it what k is, and you put in that formula we got for n2 over n1 as a formula in Mathematica. Tell it the value of k, and then you can say, if you wanted to plot n2 over n1, plot this for me for t goes from, say, 0 to 100,000 Kelvin, or whatever, and it'll make a plot for you. But if you want n2 over n1 plus n2, then you could give it a composition of functions. You could tell it that you could say this function x is equal to n2 over n1, and f of x, so x of t could be the function for n2 over n1, and then f of x of t could be that over 1 plus that, the original function, right? The x of t over 1 plus x of t. You can define the composition of function. I'm going to make you do that, so you get your Mathematica skill development going there. You could simple-mindedly just plug in a whole big formula for this. No, that is so inelegant. Do you want to be inelegant? No, you do not. You want to be elegant and use composition of functions. So, you'll think about that later, but the point is, once you know n2 over n1, you can figure out things like n2 over n1 plus n2 by this. So we've used the Boltzmann equation to get n2 over n1. 2 copies of it with a 1 plus in the denominator gives us n2 over n1 plus n2. And this is the result. So here's for temperatures between 5,000 Kelvin and 25,000 Kelvin. So at that point, would equal numbers be in N1 and N2 yet? No, because that took 85,400 Kelvin or whatever it was. I forget what was it. 86,400 Kelvin. So even at 25,000 Kelvin, right, it's pretty hot there. Look, the fraction is still under 3.5%, basically, that are up in n equals 2, right? It's a tiny fraction, What's the sun's temperature? Surface temperature of the sun, what was that about, roughly? How many Kelvin?
It's 500 million.
Oh my God, no. Oh my God, no. We'd be toast. Sun's surface temperature.
5,770.
Yeah, 5770, about 5,800 Kelvin, or even 6,000 Kelvin. So in other words, the sun's sitting about here. Are there many hydrogen atoms in the sun that are in N equals 2? No, hardly any of them. So just based on that, should the sun have strong hydrogen Balmer lines, which are made when electrons already in N equals 2 absorb photons and jump up to N equals 3 or 4? No. So in other words, while astronomers originally were thinking that that stars with weak hydrogen lines, that must mean they don't much have hydrogen in them. No. The sun is mostly hydrogen, but to get the visible hydrogen spectral lines, it needs to be to get very strong ones, you need to be much hotter than the sun is. You need to be hotter than the sun is. But then also notice we said that, remember what we said about what temperature corresponds to the strongest hydrogen Balmer lines? Roughly what? Do you remember? Temperatures of about Goldilocks and the 3 stars. What was the right temperature for Goldilocks, roughly speaking? About 10,000 Kelvin. About 10,000 Kelvin. Right around here. Are very many electrons in N equals 2 at 10,000 Kelvin? No! And yet those are the strongest hydrogen lines. The lines get weaker by the time you get to 15,000 Kelvin, or 20,000 Kelvin, or 25,000 Kelvin. Wait, what's going on here? There would be a larger fraction in N equals 2 at those temperatures. Can you remember what we were saying? What prevents getting strong hydrogen lines at temperatures that are getting well above 10,000 Kelvin? What happens to the hydrogen atoms when you get temperatures well above 10,000 Kelvin? More and more of them are ionized. More and more of them are ionized. This would be the fraction of neutral hydrogen atoms, of all the neutral hydrogen atoms, the ones that still have an electron, how many of them are in N equals 2 versus N equals 1? So at 86,400 Kelvin, according to our calculations, equal numbers would be in N equals 2 and N equals 1, if only there were electrons there in the first place. At 86,400 Kelvin, there's essentially no neutral hydrogen atoms left. They'd be completely ionized by that point. And that's why it was very important to say, in a gas of neutral hydrogen atoms, well, the answer we got is not particularly compatible with a gas of neutral hydrogen atoms. And so we have to go to the next step and consider ionization. We have to consider, okay, what fraction of the atoms would still be neutral versus ionized. And that is what Cecilia Payne did. She combined the Boltzmann equation with the Saha equation to figure out what fraction of the total population of atoms would be available for making the Balmer lines. We will essentially retrace those steps and see that it's the combination of ionization and excitation within neutral atoms. That's where 10,000 Kelvin works out to be as good as you can get. But even 10,000 Kelvin, it's still a tiny population of atoms that are in N equals 2. So I kind of lied here, in other words, when I was telling you this business of for T equals 10,000 Kelvin, a significant number of H atoms remain neutral, but are also excited to N equals 2, able to form Balmer series. Yeah, it's as significant as it gets. It's the biggest fraction as it gets. It's never very large. It is never very large. And so the hydrogen lines are kind of, in any star, not as dark as you would first think based on how much hydrogen is there. Because it's hard to make the hydrogen Balmer lines because of the fact that the second excited state, which is responsible for them, is actually quite far, 10.2 eV above the ground state. turn that into a temperature, and that's a very high temperature. And so, yeah. What questions do you have at this point? You were looking at the clock because you were hoping there was still more time before the break, more exploration and learning that you could do. It touches my heart that you didn't want that to say there was time for the break. There's a little tear.
Let's just consider it a K-type, you know?
Wow.
So like, they haven't considered about her. That she's.
Oh, yeah, that's, there's another tear streaming down my cheek, because not only do you not want it to be great yet, but you are worried about your classmate Kayla, right? Okay, wow. I don't know. I don't know if I can continue, but I'm going to try. Okay, so let's continue, shall we?
Yes.
Yes. Okay. Oh, I know. So, Willow, you're looking at that figure in your book, right, that shows, and then, here, this is what we're going to get in a minute from the Saha, several minutes from the Saha equation. Here we go. Let's point at this beautiful graph right here. Oh, look at this. Zoom in. Ooh. Oh my gosh. Linger on that. Appreciate. Oh, that is so beautiful. Okay, stop looking at it. Okay, so now, continuing our happy adventure. Right, our question is, we've already answered it qualitatively. So why are the H lines strongest at T is on the order of 10,000 K when so few H are at N equals 2 at that temperature? You would think raising the temperature would help by putting more and more at N equals 2. Why doesn't it help? It's because of ionization. So in other words, by just raising T above this, make the H1 lines weaker. Ionization rears its ugly head, or well, I guess it's ugly if you like Balmer lines, and it's beautiful if you don't. I personally don't have, well, they're lovely. I guess I do like them. So it's, yeah, thanks a lot, ionization, ruining my beautiful Balmer lines. Sure. Okay. So, as T increases, interatomic collisions become more and more violent. Become more violent. Bam, boom, bam. And photons in the ambient radiation field more energetic, right? Because you're also getting more and more energetic photons in the radiation field. Because you've still got thermal radiation everywhere. Thermal photons are getting more energetic, causing more of the atoms to be ionized. So we bring in what is called the ionization energy. The greater the ionization energy, chi sub I we call it, so that's a Greek letter chi, it's not an X, it's a Greek letter, and really we say chi, but I think it'd be better to say chi, because it's got a sound to it, and the Greeks wouldn't say I, they would say E. So even though we tend to say here in America, we say chi, it's really closer to he. But I don't know if I'm going to get myself to say he all the time. With a cat, right? Okay. The ionization energy, he, I, what did they say? He. The greater the energy, where I indicates the number of electrons that have already been removed, and because we're astronomers, we'll eventually use Roman numerals to represent I, but it's more than the number of electrons that have been removed because us. Where I indicates the number of electrons already removed. That's called the ionization stage. Ionization stage. The smaller the fraction of atoms that will be ionized, right? The harder it is to strip an electron off, the fewer electrons that will have had electrons stripped off of them. The smaller the number of atoms, that are ionized in thermal equilibrium. This is always in thermal equilibrium. In thermal equilibrium, the state of maximum entropy. Okay, well, I know this is going to be very disappointing, but it is time to take a break. I know, I'm going to force you to do it. I know you don't want to, I'm forcing you to do it. And Kayla, I'm forcing you to go to your other class. I know, it breaks your heart, I know it breaks my heart too, but it's just the way it is. Sometimes you just got to be tough. Okay, so, is that,
Why did we have to use that equation?
which one? This one right here?
The one that was next to
The
it?
one with the N1 over, N2 over N1, this one right here? Simply because we wanted to make that plot right there. In other words, it's a little more interesting to know the fraction of atoms in total that are in N2 as opposed to the fraction of atoms in total that are in N2. So that would, and so the total number of atoms is N1 plus N2 plus N3 plus N4, blah, 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 blah. But at low temperatures, there are so few atoms excited higher than N2, than N equals 2, that N1 plus N2 is a pretty good approximation to the total number of hydrogen atoms.
So they're taking fraction or the ratio of them?
Yeah, we want N2 over the total number of atoms. But the Boltzmann equation doesn't tell us that. It tells us N2 over N1, or N3 over N2, or N4 over N3, or N4 over N1, whatever, anything like that. So that was just like a trick to say, well, it doesn't tell us N1 over N1 plus N2 directly, but it tells us N2 over N1. So if I divide through, I get it in terms of what I can calculate with the Boltzmann equation. So it's practical. Just for I mean, you could make a plot of N2 over N1, but this is a little nicer. And so that's why we did that. And we'll see this show up again shortly when we're talking about ionization and stuff like that, because we're more interested in like what's the total fraction of atoms in a certain ionization stage as opposed to the ratio of that to the one in the stage below, as we'll see what we're getting here. So, okay. So, note that, I didn't say that, but note that chi sub I is the energy needed to go from the ground state of ionization stage I to the ground state of ionization state I plus 1. In other words, suppose you got carbon. If it's neutral carbon, there's all these different energy levels the electrons can have. If you strip off an electron, now there's 5 electrons that have a set of energy levels they can live in. If you strip off another, a set of energy levels that the 4 electrons can be in. So it gets super duper complicated. So the question would be, okay, am I going to go from the second excited state of ionization stage 4, where 4 electrons are gone, to the 7th excited state, some higher energy than the ground state of ionization stage 5, where 5 electrons are gone? Well, you could. So keeping things simple, we're going to go from, we're going to say that the ionization energy there, chi sub I, is the energy to go from the ground state with I electrons removed to the ground state with I plus 1 electrons removed. And then we'll see we can use what's called the partition function to account for the fact that maybe it didn't go between the ground states, maybe it went through between some other levels. So, and again, this is going to be a take my word for it. StatNet can show you where all this comes from. This is be like, take my word for it. So it's kind of like, where you learn how to do these things now, and then there's less to learn when you get to it in StatNet. So note that chi sub I is the energy needed to go from the ground state of ionization stage I, the lowest energy state of ionization stage I, where all the electrons are in their lowest energy level available to them, taking account of the Pauli exclusion principle says, oh, you can't put 3 electrons in the same spatial wave function. The ground state, excuse me, of ionization stage I electrons removed, to the ground state, so I'll put the V's in the same place, to the ground state of ionization stage I plus 1. So in other words, we might be going from the ground state of carbon with 4 electrons removed to the ground state of carbon with 5 electrons removed. The minimum energy needed to do that, to kick off 1 electron off of that carbon atom with 4 electrons removed and not disturb the other electrons. So we've gone from ground state to ground state. However, it could be that the initial and final states might not be the ground states. How rude, but it can happen. The initial and final states may not be the ground states. To account for this, we need the partition function. the partition function. And it's symbolized with a capital Z. And ever since I took German in high school, I put crossbars on my Z's. And they don't look like twos by accident. Capital Z, that's the sum from I equals 1 to infinity of G sub j e to the minus e sub j minus, that's supposed to be a j right there. J equals 1 to infinity. G sub j e to the minus e sub j minus e sub 1 divided by kt. And then I'm going to come over here and finish writing this. Because it's convenient to break it into two pieces. So for j equals 1, we've got e to the minus e sub 1 minus e sub 1 over kt. What is e to the minus? What is the base of the natural logarithms to the minus capital letter e sub 1 minus e sub 1 over kt? Well, what's e sub 1 minus e sub 1? Quick! And what's e to the minus 0? 1. So we often break this off as g sub 1 plus everything else. Because g sub 1 often dominates. It's often the most important term. So this is equal to the degeneracy of the ground state, g sub 1, plus the sum of everybody else, j equals 2 to infinity of g sub j e to the minus ej minus e1 over kt. And again, we break it into that because often G1 is the most important term. And in my notes, by the way, if you're confused by the following statement, if you look at my notes, note that as stated previously, a partition function is a Gibbs-type sum for fixed n and mu. That's a relic of, in this course, I used to do a crash course in StatMech because we didn't have a StatMech course. Now we have a StatMech course, so I don't need to have a crash course in StatMech. Although I should put the notes for that up in case you want to have them, because it is a crash course in StatMech. Quick reminder if you've never seen it or if you're curious about how it works before you, oh my God, I can't wait till I take StatMech to see where all this is coming from. You know, the notes that I can put up for. Anyway, so that little comment there. Yeah, as previously stated in the prior crash course I used to do in astrophysics. That's what that's referring to. So, in astronomical weird, right, usage, as we've already talked about, we use Roman numeral 1 to be the grounds, to be the neutral atom. So what value of I would that be? And it's important to realize here, that's why I made this a J, because I is how many electrons got removed, versus J here is labeling the energy levels within the atom. So I'm using J to mean a different thing. Yes?
We need to divide by kt.
Thank you. There we go, yes. Friggin' dividing by kt. Yes. Thank you for pointing that out. What's the matter with me? Oh, I'm just trying to see if you're paying attention. You win! You win! Okay. Yes. So, we use a Roman numeral 1 for the neutral atom. Remember, I is the number of electrons removed. So if it's a neutral atom, how many electrons have been removed? None of them, right? So Roman numeral 1 means ionization state, I equals 0. No electrons have been removed. The neutral atom. 2 equals 1 electron removed. So I is equal to 1, right? Etc. Right? So we have our weirdo notation where the Roman numeral is 1 more than little I, 1 more than the number of electrons removed, because we're weird. Here's a problem. Strictly speaking, in general, Z diverges. That sum doesn't converge. It is infinite. In general, Z diverges to infinity. The sum is equal to infinity, which wouldn't be very useful. Consider hydrogen to see why. Consider hydrogen as N, well, okay, I'll put it like this. I have it as J in my N. So I'm using J here to generically represent energy levels in what could be multi-electron atoms. And in that case, we can't just use a simple number N for a single electron to represent what energy level it's in. So we use a more generic J as just a label that's counting the different states, but that could correspond to, the first 2 electrons are in N equals 1, but the second electron is in N equals 7 in this weird lithium atom, for example. But if it's hydrogen, J and N become the same thing. If it's hydrogen, J, labeling the energy levels, is the same as the principal quantum number here. So as J, which is what we're calling N, if it's hydrogen, as J goes to infinity, so it's really, as J goes to infinity with a parenthetical comment there, as J goes to infinity, G sub J, what's G sub J? What's the degeneracy for hydrogen? It's 2 hydrogen degeneracies in terms of N, it's 2n squared, but here we're calling it J, it's generic, it's 2J squared. G equals 2J squared. Where does that go as J goes to infinity? As 2J squared, let J approach infinity, what does 2J squared approach? Infinity, right? 2J squared approaches infinity. So the G's approach infinity as J goes to infinity. They get arbitrarily large. While E sub J minus E sub 1 approaches what? So remember that, again, if we're using J as the label here, E sub J is minus what over what? How many electron volts over what? He said, getting them to memorize that oh so important formula so that in the future when I say it, why, without even thinking, their knee jerks up because it's a knee-jerk reaction. What is it?
13.6 over N squared.
Yeah, except we're calling it J, so it's minus 13.6 EV over J squared because we're calling it J, just to be obstinate here. So not really, just because I'm using J as a generic whatever. For hydrogen, E sub J goes to, is equal to minus 13.6 over J squared. So EJ goes to where as J goes to infinity? Right, so this goes to what as J goes to infinity? As J goes to infinity, what does E sub J go to? 0, right? Because as every physicist knows, if you divide by infinity, that's equal to 0. Don't tell Dr. Nunemacher, but it is, okay? So this, he would agree that it approaches 0 in the limit. He just wouldn't let you say, if you divide by infinity, it's equal to 0. No. As you go, right, in the limit, blah, blah, for every epsilon, there's a whatever, right? It's 0 for him, okay? That goes to 0. So E sub J minus E sub 1 goes to 0 minus 13.6 electron volts equals 13.6 electron volts. So E sub J minus E sub 1 goes to 13.6 electron volts as J goes to infinity. So E to the minus E sub J minus E sub 1 frickin' over KT goes to some finite value. Some finite non-zero value. Doesn't go to 0. Right? So I know that, what is it, Calc 2? Is it, which calculus class do you study infinite series in? Calc 2? I know your favorite topic in Calc 2 was like infinite series and whether or not they converge and stuff like that. Yes. 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 You know it, right? And so you can look at this and say, okay, I'm adding a bunch of terms where this piece is going to infinity and this piece is staying finite. And when you add an infinite number of terms that are all going to infinity together, the result is infinite. In other words, this sum blows up and doesn't converge because I'm adding something that goes to infinity times something that stays finite. So that's going to blow up. Going to blow up good, right? So, boom! So Z goes, boom! It blows up, which would limit its usefulness. However, and this is best left to the professionals, which is why when you actually see homework problems in the book, they're basically going to say, and the result of the calculation is, but I want you to see qualitatively here. Here's the thing. We haven't mentioned this, but you may recall that in the Bohr model, r sub n, the radius of the nth Bohr orbit, is actually proportional to n squared. And if you do it in the quantum mechanical version, the expectation value of the radial coordinate of the electron, it's proportional essentially to n squared. The higher the energy level, the further the electron likes to be from the nucleus. And so that means that for n large enough, your hydrogen atom, in the Bohr model, that electron's orbiting a meter from the proton. Or for an even larger n value, it's orbiting 3 kilometers from the proton. Why, there's an n value where the electron is orbiting 7 million light years from the proton in the center, et cetera, et cetera. According to the Bohr model or to the Schrodinger model, a hydrogen atom can get arbitrarily large. And if there was just one hydrogen atom in all the universe, in principle, it could get that large. But could you have a hydrogen atom that is a centimeter across in this room? The answer is no. Why not? What would keep a hydrogen atom from being a centimeter across in this room? Yes.
interaction with other.
Yeah, right? The air molecules that it's interacting with, they're way less than a centimeter apart from one another. There's no way an electron could be orbiting, quote unquote, a centimeter from a proton in this room. It's free at that point because there's no way any of those other atoms are going to let that thing just, oh, here I am, I'm being an orbital rather, right? You know, that ain't happening, right? And so the idea is that we really have to put another term in these sums that represents the probability that that level has been perturbed out of existence by interactions with other atoms and particles and so forth. Which means, effectively, the sum gets truncated before it blows up to infinity because the higher level terms are from things that don't exist. That you're just not realistically going to get any atoms in those states. That's the idea there. So, however, to make this all an official way, the orbital radius, which really would be the orbital radius in the Bohr model and the Schrodinger model, it's okay. Some expectation value, I'll just leave it at that. Approaches infinity as J approaches infinity. So only for a sad, isolated atom alone in the universe, all by itself, crying because atoms can cry, could all the states contribute to Z? Really, we need to multiply each term in the sum by the probability that it has not been perturbed out of existence. We need to multiply each term in Z by the probability that it has not been perturbed out of existence. And I'll put that in quotes. It has not been perturbed out of existence by interactions with other particles, with other atoms, electrons, etc. And I'll just add, this is a job for the probes. We're not going to try to do that. We're going to allow Carol and Osley to wave chicken feet and say, and it turns out the partition function is blah, right? And we'll just take their word for it. I mean, I've never tried to do one of these calculations myself. It's for the pros. So, what questions do you have at this point before we write down the Saha equation? This is an exciting moment. You see the Saha equation, not just Boltzmann, but Saha. I mean, it would be convenient if there was some brilliant Indian physicist who could come up. Oh my God, there was. So, if I'm saying his name wrong, tell me. S-A-H-A. Now, of course, that's a transliteration.
So, is that not an actual name?
No, it's a name. It's an actual name now.
Yes, so it's actually right.
Oh, cool, okay.
You're cool.
Wow, nice. Because I thought you were going to say, oh, no, actually it's Saha or something like that. Right. But then we go up, aha, Saha or something like that, right? But now we'll just say, aha, Saha.
Right.
Yes, okay. Here we go. Our Saha moment. The Saha equation is, thanks to Magnet?
Yes.
Okay, so
Let's make
Magnet, okay. 1920. Ni plus 1 over Ni. So number of atoms in ionization stage I plus 1, they've lost I plus 1 atoms. And this is of a particular species like carbon or praseodymium or whatever, some particular atomic species. Ni plus 1 over Ni, number that have lost I plus 1 electrons over number that have lost I electrons, is equal to 2, which turns out to come from the two spin states for the electron. And I did, so I think I've still got those notes I get close to, because one day I thought I should derive this, so I did. So if you want to see where this comes from, you can see that too, although you have to read other stuff to get to that point. 2, too bad I didn't do it first, you know. 2 times Zi plus 1 over Ne times Zi times MEKT over 2 pi h bar squared to the 3/2 power e to the minus chi sub I freaking divided by kt. And it's important, so it needs a box around it. And we have to say what the symbols mean that we haven't defined yet. So we've already basically said n sub I is number of atoms in ionization stage I. We're going to say number of items, chemical species in question, right? Not atoms in general, but like carbon atoms, praseodymium atoms, lead atoms, whatever it is. The number of atoms of chemical species in question in ionization stage I. We've lost I electrons. And N sub E is the electron number density. So we're going to see a lot of examples of number densities as we continue forward. A number density is a number of particles per cubic meter, per unit volume, basically. So as opposed to mass density, kilograms per cubic meter, number density is particles per cubic meter, or whatever your unit volume is. So number of electrons per unit volume is the number density of electrons. So in SI, the units of number density are inverse meters cubed, right? Per cubic meter, meters to the minus 3. And so again, this is very much, we're just taking word for it, right? We haven't derived this in any way, but we should talk about its plausibility, that it implies things that we think it should. So first of all, just to note the extreme sensitivity to chi sub I, since it appears in the exponent, right? As chi I increases, this ratio decreases exponentially as the ionization energy increases. So note the extreme sensitivity to chi sub I, since it is in the exponent. So that's one thing to note. As the ionization energy increases, that really suppresses the number of atoms that'll be in that ionization, that'll get ionized to the next level, essentially. The higher the ionization energy, the harder it is to strip an electron off, is really what that's representing. Chi sub I is how much energy it takes to strip one electron off, going from the ground state of stage I to the ground state of stage I plus 1. You remove one more electron. The more energy that takes, the harder it is to do, the less will have been promoted up to stage I plus 1. So that should make some intuitive sense. Harder, more energy to ionize means less of them get there. So we'll say that, I guess I'll add some words, right? So this is saying, I can put this in English, this is saying that the more energy is needed to go from stage I to I plus 1, more energy is needed to strip off one more electron and go from stage I to I plus 1, the fewer atoms will be in stage I plus 1. The fewer the number of atoms that will be in stage I plus 1. But again, it's an exponential decay. If you were to somehow, the ionization energies or the ionization energies are not knobs we can turn, but if you imagine that they were, boy, dialing up that ionization energy sure does dial back the number of atoms that reach that ionization stage. Okay, does that make sense intuitively? The harder it is to strip off an electron, the less atoms will have that extra electron stripped off. That's really what that's saying. And it's saying, well, it's really hard. It's really freaking hard because it's E right there, right? So that exponential, e to the minus I over kT. What happens as T increases? As T increases, intuitively, as T increases, before you even looked at this equation, if T goes up, what should happen to the ratio of atoms that have lost I plus 1 electrons to the number of atoms that have lost I electrons? Does increasing the temperature make more atoms more highly ionized or fewer atoms more highly ionized?
More atoms ionized.
More, because the higher the temperature, the more energetic the collisions, the more likely it is you kick an extra electron off of an atom. So as T increases, Ni plus 1 over Ni should increase, and that happens because as T increases, this negative exponent gets smaller, which will make e to that power get bigger, right? E to the smaller negative number is going to be bigger than e to some really huge negative number, right? E to the minus 1 is much larger than e to the minus 7,000, right? So decreasing the magnitude of chi I over kT by raising t will increase e to the minus chi I over kT. So mathematically that does work out. And if you're not convinced of that, think about that carefully. So note that as T increases, Ni plus 1 over Ni increases as expected. If this equation said otherwise, we have to fix it. So as T increases, you're getting more and more highly ionized atoms. That should be true. I should pause so people can catch on. As much as what questions do you have? Because if that doesn't make sense to you, just ask me now. Are you at peace with this assertion? Are you at... Okay. From a pure math perspective, as the electron number density goes up, what happens to Ni plus 1 over Ni? Goes down. So now, does that make sense? Well, if you're an atom that is missing some electrons, are you positively charged or negatively charged? If you're missing, you're positively charged. Does that mean you just might be tempted to combine with an electron if you happen upon it? And if there's more electrons around, might you happen upon them more often? And so, if there's more electrons around, might it be more likely that Ni plus 1 atoms get turned into, that I plus 1 stage atoms gets turned to stage I atoms? Because if stage I plus 1 adds an electron, it decreases the ionization stage by 1, right? Because the ionization stage, how many electrons will be removed? Well, if I combine with an electron, I drop down to the next lower down ionization stage. So electrons take atoms in I plus 1 and convert them into I. So the more electrons there are around, the fewer will be in Ni plus 1 compared to Ni, because they're busily turning I plus 1 ions into I ions, so to speak. So that's the intuition, is that the bigger Ne is, that will favor unionizing, if you will, atoms that are in I plus 1 and turning them back into I. So that'll push the equilibrium towards I as opposed to I plus 1. It'll reduce the ratio of I plus 1 to I atoms intuitively. So we describe that with note 2 that Ne appears in the denominator He appears in the denominator. This makes sense. That's plausible. Since having more electrons available for potential recombination, which is what we call it when an ion recombines with an electron, and if you took cosmology, you know that, of course, we call the very first time that electrons combined with protons to form atoms in all of the universe's history, the epoch of recombination. The very first combination is recombination. Okay. Yay, anyway, this makes sense. So, we're astronomers, right? So why would we name it logically? Why would you do that, right? So anyway, this makes sense. Since having more electrons available for potential recombination will push the balance in favor of state I. Having more electrons available for recombination will push the balance in favor of state I. And so here's something that we don't see directly in the equation, but in general, some atoms are really good at holding on to their electrons, and some atoms are not. If you have atoms around which are not very good at holding on to their electrons, that tends to make Ne larger. There's more electrons stripped off of them, which suppresses the ionization of everything else, because those extra electrons from the easily ionized species can then also push down the ionization of other atoms. So, in other words, note that all the atomic species contribute to Ne. It doesn't matter where those electrons came from. It doesn't matter if it came from a carbon atom or a praseodymium atom, and electrons and electrons and electrons. All the atomic species present contribute to Ne. So the presence of easily ionized species tends to suppress the ionization of other species. They want all the ionization fun to themselves, and so they make it harder for other species to be ionized. Jokes. So like, what would be an easily ionized species? Think chemistry here. If you dissolve salt in water, first of all, what is salt? Salt is NaCl, it's NaCl. It's sodium chloride, right? So you dissolve salt in water, and what happens? You got Na, you got Cl, they don't stay neutral. Which one becomes positive and which one becomes negative?
Na becomes positive.
Yeah, Na becomes positive, Cl becomes negative, and that's because sodium has one loosely held electron in its outermost shell, and chlorine is just dying to add an extra electron to its outermost shell. In other words, chlorine is very electronegative. It loves binding with an extra electron. And sodium is like, you know what, I don't really need all these electrons, so to speak, right? So in other words, which one of these is easily ionized? Which one easily loses electrons? It's sodium. Well, that would be true also. Sodium in a stellar atmosphere, it's easily ionized, and so its presence donates electrons that tend to suppress other species getting ionized. And this shows up in stellar atmospheres. This is jumping ahead, but the sun looks like it's got a solid surface in photos, right? It looks like it's got a nice sharp edge. And that's because it has a layer that we call the photosphere, where the photosphere is about 400 kilometers thick, meaning that a photon can only typically go around 400-ish kilometers before it would get scattered by a particle within the photosphere and turn it around. It means that for photons coming out of the sun, for the most part, they scatter last within that layer about 400 kilometers thick before they fly off into outer space, never to return. And so it looks to us like the light is coming from this 400 kilometers thick, sounds like a lot, but the sun's diameter is 696,000 kilometers. I'm sorry, its radius is 696,000 kilometers. 400 kilometers is a tiny fraction of that. Also, from the Earth's surface, the resolution of telescopes is like 700 kilometers, which is more than the thickness of the photosphere. So the sun looks like it's got a sharp edge to it. And that took a while before people realized, no, the sun's a fuzzball. Right? right? It's gaseous, it doesn't have a sharp edge. What's going on there? So, just like chlorine can add an extra electron and become Cl minus instead of hydrogen, hydrogen can add an electron and become H minus. Now, if you just have hydrogen hanging out, a bunch of hydrogen atoms, they're not going to be, and nothing else, they're not going to become, none's going to become H minus, because to get that H minus, which is weakly bound, an extra electron, you'd have to rip off the tightly bound electron off some other hydrogen and give it to the hydrogen becomes H minus. So a gas of just hydrogen atoms, you're not going to make H minus. But the sun doesn't have just hydrogen in it. It's got other atoms as well, including species which hold their electrons a lot less tightly than hydrogen does. So those species produce free electrons, and some of them bind with hydrogen atoms to make H minus. And in cool stars like the sun, H minus is the primary source of opacity at visible wavelengths. It's the primary atomic species which makes it hard to see into the sun, because it's really easy to kick that H minus off. Every visible wavelength has enough energy to kick the electron off H minus, which means H minus is really good at stopping visible light photons in their tracks. It can eat them and strip the electron off. And so that's why the sun seems to have a surface to us, why it looks like it's got a sharp edge. Because easily ionized species donate electrons to the milieu, and then neutral hydrogens can become H minus that way and be really good at absorbing light. And so that's a fundamental fact about the sun. This H minus is so important in the sun and other similar stars. Stars which have a lot less heavy elements in them don't have as many free electrons around. H minus is less abundant, and those stars, you can see deeper into them and they look hotter, as we'll see. A star the same mass as the sun, but that is older, so that the universe hadn't made as much other things besides hydrogen and helium, will have less H minus in its atmosphere, which means we'll be able to see deeper into it, and so it effectively will have a smaller radius and higher surface temperature than the sun. And this is the reason why the main sequence in old stars is a little below the main sequence in younger stars like the sun. It's really shifted to higher surface temperatures because of that. So, more to come, but since we only had a couple of minutes left, I thought, oh, well, I'll just tell a little story here to whet your appetite for more to come. Before next time, we all become Cecilia Payne and we show why it is that hydrogen lines are strongest at around 10,000 Kelvin and not at other temperatures. And it's really the temperature and not the hydrogen abundance that's the important thing there. And then we too can feel the thrill of rediscovery of how that works. But I think that's pretty cool. I mean, it's a really cool thing to trace out there. So now imagine being the first person to do it. Right? Wouldn't that be amazing? Right? So who knows? Maybe someday you'll be the first person to do something. All right.